An increasing function is a function with a graph that increases as you move from left to right. The y values increase as the x values increase. So think about, from the beginning of this chapter, direct variation. As the x values get larger, so do the y values. A decreasing function is a function with a graph that decreases as you move from left to right. The y values decrease as the x values increase. So you could think back to the beginning of the chapter to the inverse variation functions. Larger x values lead to smaller y values. A constant function is a function with a graph that stays the same as you move from left to right. The y values do not change as the x values change, or as the x values increase. It'll appear like a flat horizontal line. For the following, on the next example, we're going to talk about domain intervals and break it down and talk about where is the function increasing, decreasing, and staying the same. So on example 1, increasing, well, it's increasing from here, and there we have an arrow, so it starts increasing at 3, and it continues increasing forever. That's what the arrow implies. It decreases between here and here, and so that's from the x values from 2 to 3. And then it remains constant during this flat piece from -5 to 2. And I'm identifying these things because increasing means it's going up from left to right. It's headed in an upward direction. Decreasing means from left to right it's going down. And constant means it's horizontal. There's no change in y value. So for the next one, where is it increasing? Well, it starts off increasing. So from there to there. So from -3 to 1. It's decreasing over here, going down from 3 to 5. And in the middle is where it's flat and horizontal. So from 1 to 3, it's remaining constant. On the final graph, it's increasing on the far right-hand side. So it starts increasing at 6, and this arrow means it goes on forever. It's decreasing. Oh, you know what? We have another increasing interval also. So let's move this over a little. It starts out increasing as well. We've got the arrow here. So it's increasing from -infinity up to 2. And then from 6 to infinity. This graph actually is not decreasing anywhere. We don't see any portion of it headed down from left to right. But it does remain constant right in between. So from 2 to 6, it remains constant. And we don't have anywhere that it decreases. Number 4 asks us to sketch a graph for the situation described below and label key information. So it says the temperature in degrees Fahrenheit during a snowstorm slowly decreased at the start of the storm, reached its coldest halfway through the storm, quickly rose above the temperature at the start of the storm, and then decreased to the temperature at the start of the storm. So slowly decreased means we need to come down with a shallow slope. We're going to reach its coldest point halfway through. And it's going to rise quickly, so we need a steeper slope and go above where it was before. And then it's going to decrease back down to where it was at the beginning of the storm. So this is the end of the storm. This is the start of the storm. On the x-axis, we have temperature in degrees Fahrenheit, and on the x-axis, it's time. So here, about halfway through, is where we reach our lowest temperature. Here's the start of the storm and the end of the storm. So something along those lines would be fine. You just need a more shallow slope to show the slowly decrease. Quickly increase means a steeper slope going up. And then it has to come back down to about where you started. Okay, average rate of change. For a linear function, the rate of change is constant, and it's known as the slope. Even for a nonlinear function, however, we can find the average rate of change over any interval by finding the slope of the segment that connects the points on the graph determined by the endpoints of the interval. So given the interval from one x value to another x value, the average rate of change can be found using the slope formula. Remember, this is the same as the slope formula we learned in Algebra 1. We find the difference in the y values divided by the difference in the x values. They just used function notation here. So these two are the exact same. So they'll give us a domain interval, they'll give us two x values that we need to find the average rate of change in between. So we'll need to calculate the y values if we don't already have them. Find the difference in the y values and divide it by the difference in the x values, just like we always do for slope. It's just that we're going to find slope of these little tiny pieces connecting certain points rather than the entire graph, because the graph is not linear, it's a curve. So number 5, find the slope of the line segment that connects the indicated points. So from A to B, that's this segment right here. Well, the points are 1, 0, and 2, 1, so we find our average rate of change by finding the difference in the y values. So 1 minus 0 divided by 2 minus 1. So we get 1 over 1, which equals 1. For BC, that's this segment right here. Same thing, find the difference in the y values. So 2 minus 1 over the difference in the x values, 4 minus 2. So we get 1 over 2, or 1/2. So we can see it's becoming more shallow. CD is this one right here. Difference in the y values, 3 minus 2 over 8 minus 4. So we get 1/4, even more shallow. And we can see that it's becoming closer and closer to horizontal. So our last interval from D to E, difference in the y values, so 4 minus 3 divided by the difference in the x value, 16 minus 8. We get 1/8. So we can see that the average rate of change is decreasing by 1/2 each time. It started at 1, then it's down to 1/2, then it's down to 1/4, down to 1/8. It's becoming more and more shallow, less steep, and it's approaching horizontal. It's approaching a constant. Read. For our next example, they give us the function but not the graph or the exact ordered pairs. So we're going to have to use this rule to find our outputs or our y values. We're asked to find the average rate of change over the intervals -2, 0, 4 to 6, and 6 to 8, and then discuss what happens to the average rate of change as x increases, and what that would mean for the graph. So first of all, the last one we did was a logarithm, so its graph we know, it increases sharply on the left side and then it levels out and approaches a constant looking horizontal line. On this one we've got an exponential function, so we expect this time it's exponential growth since the base is 2, so we expect it to start off pretty shallow, almost horizontal, and then shoot upward at some point. So we'll keep that in mind as we find our average rate of change. Okay, so this is a domain interval. These are x values. So they want us to find the average rate of change, or the slope, between x values of -2 and 0. The thing is, we need y values for that. So the first thing that you have to do is find your y values. Find f of 2, so f of 0. You're going to subtract from it f of x sub 1, which is -2. And we're going to divide that by 0, take away the -2. So we actually have to go through and do the calculations for the y values. F of 0 means you're going to replace the x in the rule given at the top with 0. You're going to figure out what that is. You're going to subtract from it the value you get when x is -2. In the denominator, 0 take away -2 is really 0 plus 2. So in the top we have 2 to the -2nd, which is 1/4, plus 1 gives us 5/4. We're going to subtract from that 2 to the -4th power, which would be 1/16, plus 1 gives us 17/16, all divided by 2. Well, we can turn this into 16ths by multiplying by 4/4, so this is the same as 20/16. So 20/16 take away 17/16 gives us 3/16 divided by 2, which is the same as 3/16 times 1/2. So we get 3/32. So our average rate of change for that domain interval is 3/32. Now we do the next one. So we want the average rate of change between the x values of 4 and 6. So we have to find f of 6 minus f of 4 divided by 6 minus 4. So f of 6 means 2 to the 6 minus 2 plus 1. Gotta figure out what that is and subtract from it f of 4, which is 2 to the 4 minus 2 plus 1. 6 minus 4 is 2. So in the top, we have 2 to the 4th power plus 1 minus 2 to the 2nd power plus 1. Well, 2 to the 4th is 16 plus 1 is 17. 2 squared is 4 plus 1 is 5. So we get 12 divided by 2, or 6. Next domain interval is from 6 to 8. So we gotta find f of 8, take away f of 6, and divide it by 8 minus 6. Okay, well f of 8 means 2 to the 8 minus 2 plus 1 over 2 in the denominator. We gotta subtract f of 6, so 2 to the 6 minus 2 plus 1. So that's 2 to the 6 plus 1 minus 2 to the 4th plus 1, all divided by 2. Well, 2 to the 6th power is 64 plus 1 is 65. 2 to the 4th is 16 plus 1 is 17 divided by 2. This gives us 48 divided by 2, or 24. So we can see that the average rate of change is increasing by a multiple of 4 as x increases. We can see that in these final two. These final two are consecutive, and the value increased from 6 to 24. So it was 4 times as steep in the end. It started off really shallow as we expected, and then it's getting steep very quickly because we know that in general this graph is going to look something like this. So it starts out pretty shallow, almost horizontal, and then it's going to start shooting upward. Remember, all I'm doing is I'm using this to find my y values, because these are domain values. These are all x values. This is x1, this is x2, and so I need my y values to calculate slope. So in this first example, I figured out that when x was -2, the y value was 17/16. And I got this from this formula. When I plugged in -2, I had 2 to the -4th plus 1, which is 1/16 plus 1, and 1 is 16/16. So I got 17/16. So that was my y value. That corresponded to the x value of -2. And then I did the same thing to find the y value for x value of 0. I got 5/4 because I did 2 to the 0 minus 2 plus 1, or 2 to the -2nd plus 1, which is 1/4 plus 1, and 1 is 4/4. So it gave me the 5/4 for my y value, so that I could find the difference in the y values and divide it by that difference in the x values. So I really am just applying the slope formula. I just have to do some algebra to find the y values. So here's another example of average rate of change. This time they're giving us the function negative log base 2 of x. And we're going to find the average rate of change for the intervals 1/8, from 1/8 to 1/4, 1/4 to 1/2, and from 1 to 2. And then we're going to talk about what happens to the average rate of change as x increases and what that means for the graph. This is a logarithm, so we expect the parent function of a logarithm is moving up very quickly and then starts to level off and become much more shallow and almost horizontal. But we have a negative a value here. So it's going to give us an x-axis reflection. It's going to change the orientation. So I'm going to expect it to decrease really quickly and then level off. Alright, so for my average rate of change, I've got to find f of 1/4 minus f of 1/8 and divide that by the difference in the x values, so 1/8 minus 1/2, because remember this is x1, y1, or sorry, x1, x2 not. They don't give us the y values, so we have to calculate those. So these are two x values. Alright, so I calculate the y values by using this function. When I plug in 1/4 to that function, I have negative log base 2 of 1/4 and minus negative log base 2 of 1/8, all divided by negative 1/4. Well, let's do that step by step. So if we get a common denominator, 1/4 is the same as 2/8. Alright, so log base 2 of 1/4, well, that's -2, because we'd have to use a negative exponent to get the 2 in the denominator, and then square it to get 4. So we've got negative 2 minus the opposite of the log base 2 of 1/8. Again, we know it's a negative to get the 2 in the denominator, and 2 cubed is 8. So it's the opposite of -3. All of this over positive 1/8. Okay, so it's really positive 2 minus positive 3 over 1/8, or negative 1 over 1/8, but we never divide by a fraction, we multiply by its reciprocal. So this in the end is going to give me -8. That's my first average rate of change. So as I expected, it's decreasing very quickly. Same thing for the next one. So we've got to find f of 1/2 minus f of 1/4. So we have 1/2 minus 1/4. So we've got the opposite of the log, base 2 of 1/2 minus the opposite of the log, base 2 of 1/4, all over, well, I need a common denominator, so 1/2 is 2/4, take away 1/4. The log base 2 of 1/2 is -1, so we've got the opposite of -1 minus the opposite of the log base 2 of 1/4 is -2, all over 1/4. So this is really 1 minus 2 over 1/4, which is -1 over 1/4. Again, we don't divide by a fraction, we multiply by its reciprocal. So in the end, we get -4. For our last domain interval from 1 to 2, so f of 2 minus f of 1 divided by the difference in the x values, so 2 minus 1. F of 2 would be the opposite of the log, base 2 of 2, minus the opposite of the log, base 2 of 1, all over 1. So the log base 2 of 2 is 1, and the opposite of that is -1, minus the log base 2 of 1 is 0. We can't have a -0, so it's really just 0. And so we get -1 divided by 1, which is -1. So what we can see is happening is it's going down. It's half as steep, and then we jumped in our interval from 1/2 to 1, so we can see that it's just half as steep each time. If we calculated the one in the middle, we'd expect it to be -2, and then it comes down to the -1. So as x increases, the average rate of change is decreasing by half. If you think about just the numbers, the 8, the 4, the 2, the 1, or if you think about it in terms of negative, it's decreasing less and less, and it's approaching the horizontal line. So what does this mean for the graph? Well, as we expected, it's a logarithm with a negative a value, so it's got the flip in orientation, so it's going to appear something like that. So please remember that average rate of change is just slope. You're calculating the slope on domain intervals. Because we have a curve, it does not have a constant rate of change. Therefore, it doesn't have an actual slope value for the entire graph, but we can break it down into these little segments and calculate their average rate of change the same way we would find the slope of any line. You're going to calculate your y values, so that's what we're doing in the top there. Find the difference in those two y values and divide it by the difference in the x values. And then we can compare them and talk about what's going on with the graph. One of the other ways we can describe a function is in regards to its symmetry. So there's two different types of symmetry we can talk about. Even functions, which have symmetry with respect to the y-axis. And so if we would replace x with -x, or the opposite of x, we'd get the same exact output. There'd be the same y value on both sides of the y-axis. So this point and this point have the same y value. One's just positive x, like maybe x was +2, and the other one's -x, so maybe x was -2. Both gave you the same exact y value, maybe it's 3. So maybe this point is 2, 3. This one would be negative 2, 3. So even functions are symmetric about the y-axis, meaning the y-axis cuts them directly in half. Then there are the odd functions. The odd functions have symmetry with respect to the origin. On replacing x with negative x, we'd get the opposite y value. So the y value for negative x is equal to the opposite of the y value for positive x. So if we have the point 2, 3, then negative 2 would give us negative 3. So here the symmetry is the origin. You'd have to think about flipping all of your points over the origin to find their matching point. We use those properties that for even functions, negative x gives us the exact same output as regular x, and that for odd functions, negative x gives us the opposite output as positive x, to determine from an equation whether functions are even or odd. And if we just get a completely different output, then they are neither even or odd with regards to symmetry. So please remember this is different from even or odd with polynomials. When we studied polynomials, we talked about the idea that if you had a highest degree, highest exponent that was an even number, we called it an even function, and we knew both ends went up or both ends went down. If the highest degree or highest exponent was an odd number, then we said it was an odd function, and we knew one side would go up, the other side would go down. This is completely different. Now we're discussing even and odd versus in regards to symmetry. So even functions with regards to symmetry, you can fold them perfectly over the y-axis and they'll match up. Odd symmetry means that all the points are reflected about the origin. So let's apply our tests. Number 7, f of x equals x cubed minus 7x. So let's see what happens when we replace x with the opposite of x. So we have the opposite of x cubed minus 7 times the opposite of x. Well, if we take negative x and cube it, we're going to get a negative output. If you multiply a negative 3 times, it'll come out negative. Negative 7 times negative x, that will give you positive 7x. So what we notice is the first term switch signs, the second term switch signs, which means that f of negative x was equal to the opposite of f of x. So this would be an odd function with regards to symmetry. If we graphed it, all of the points would be reflections of one another about the origin. Number 8, g of x equals 6 divided by x plus 1. Let's see what happens when we plug in negative x. So we get 6 over negative x plus 1. Well, the 6 stayed the same, so did the plus 1. The only thing different is the x is now negative x. So this is a case of neither because everything didn't flip. Just the sign of the x. Number 9, f of x equals the opposite of x to the 6th plus 3x to the 4th minus 2x squared minus 7. So when we plug in negative x, we'll have the opposite of negative x to the 6th power plus 3 times negative x to the 4th power minus 2 times negative x squared minus 7. So we have the opposite of negative x to the 6th power would come out positive. Because if you multiply a negative an even number of times, those negative signs will all pair up and cancel out. 3 times negative x to the 4th, well again, negative x to the 4th would come out positive, so it'll be positive 3x to the 4th. Negative x squared would come out positive, times the negative 2 gives us negative 2x squared, and then minus the 7. So you see the first term stay the same, second term stay the same, third term stay the same, fourth term stay the same. So f of negative x is equal to f of x, meaning that with regards to symmetry, this is an even function. The y-axis would perfectly cut it in half. Number 10. So f of x equals negative 5x divided by 12 minus x squared minus x to the fourth. Let's replace x with negative x. So in the numerator, negative 5 times negative x gives you positive 5x. In the bottom, we have 12 minus negative x squared would come out positive, minus negative x to the fourth power would also come out positive. And so we see the denominator stayed the same, but the top flipped. So that means then that it would be considered odd, because if only the numerator switches, that means your sign has switched. This has the opposite sign as the original, because you could factor the negative out on the original and think of it as negative 1 times 5x over 12 minus x squared minus x to the fourth, which is the opposite of positive 5x over 12 minus x squared minus x to the fourth. So this one is odd. If both the numerator and denominator changed, then we'd be able to factor the negative out of both the numerator and denominator. They'd cancel, and it'd be an example of even. Or if just part of that denominator had switched and nothing else, then it would be neither. But since the numerator completely changed signs, it is the opposite sign of what the original was, so this is a case of odd. In general, if, all of your signs flip, if we don't have a fraction, then it's odd. If everything stays the same, then it's considered even. If only part of it switches, it's considered neither. So in this case, the 1 would have had to change signs too in order to make it odd, or the 6 and the 1 would have to change along with the x in order to make it even and have it all cancel. Or in this case, the numerator changed, which was enough to change the sign so that it's opposite sign of what we had before, so it's odd. Again, this is talking about even, odd, or neither in regards to symmetry. Even functions are symmetric about the y-axis. Odd functions are symmetric about the origin. And then neither could have symmetry about something else, or just no symmetry at all. But this is how we test for it. If you're asked whether it's even, odd, or neither in regards to symmetry, plug in negative x, simplify, and see what you get. See if your answer is the opposite of what you got when you plugged in positive x. In that case, it's odd. See if it's the same as what you got when you plugged in positive x. In that case, it's even. Or if it's just neither of those two.